So, hello everyone. Today we are going to start week 6, that is kinetics of substrate utilization, product formation and biomass production in cell culture. So, we can quickly recall what was discussed in the last module. It was microbial growth kinetics, then how to model this growth kinetics. The simple one was discussed, this monod model. Then further we discuss transient growth kinetics, and in addition we discuss in many times during the growth kinetics there may be substrate or product inhibition, and finally in the last lecture we discuss various primary and secondary metabolites. So, in today's lecture, continuing from the last module, we will be discussing mostly today on structured kinetic models, and there we are going to discuss these two models. First is the compartmental models and second is the model of cellular energetics and metabolism. So, if you can quickly remember this, we can divide this cell population kinetics into structured, unstructured, segregated and unsegregated. So, when we assume this balanced growth approximation, so that is called unstructured model. So, today we are going to discuss this structured model, means we are not assuming the balanced growth. So, if you remember, in the case of unstructured model, we are assuming or we are treating cells as black box, in which there is a input and there is a substrate is coming and product is going out. For example, typically if you just see the monod kinetics, mu equal to mu max S upon Ks plus S. So, it is not giving any information about dynamic behavior of the system, rather it is considering cell as a black box, there is certain input and there is product as output, and it assumes the constant biomass composition. Further it predicts this mu x and yield, because they are the external parameter, how much substrate consumed and how much biomass is formed or how much product is formed. So, what are the limitation of unstructured model is, it is unable to predict the dynamic behavior of the cell subject to the external conditions. So, which are the behavior? First is intercellular pool variations like this DNA, RNA and proteins, dynamic and transient adaptations like lag phase, transient nutrient shift, and third is the product formation when it is linked with physiological states. So, these are the limitations which cannot be predicted using unstructured kinetic model. But at the same time it is also not possible to model all the reaction within the cells, because thousands of reactions are ongoing. So, one option is there, we can group these reactions based on their characteristic time constant or relaxation time. And if you see this based on the relaxation time, we can divide this temporal organization into three systems: genetic system, epigenetic system and metabolic system. So, time scale for genetic system is in the order of generations. So, you can say in the order of hours to days, that is the genetic system. It is the longest time scale, it has a longest time scale and associated with changes in DNA composition, it may be due to mutation or gene transfer. The next system you can consider is epigenetic system. It has intermediate time scale and it is related with DNA transcription and followed by translation. and enzyme induction. So, for this transcription, translation and enzyme induction, the typically time scale is about 10 minutes to 1 hour. The third system you can consider as a metabolic system. So, it has a very short time scale, and few example includes enzyme catalysis, metabolite turnover, and the typical time scale is in the seconds to minutes. Now, considering these three relaxation times, let us say if I talk about this enzyme catalysis. So, in the case of enzyme catalysis, there will be transcription and translation which lead to the synthesis of enzymes, but the transcription and translation will take the time, let us say in the minute, while this enzyme catalysis it will happen in the order of seconds, right. So, in that case what we can do, we say that this transcription and translation, or you can say enzyme synthesis part, can be considered as a constant. However, if you think either way, if the changes occurring in the external environment are at the time of epigenetic system. So, if it is matching with this 10 minutes to hour, so in that case this metabolic system which is happening at the time scale of seconds is considered to be in the quasi steady state. Now, then what is structured kinetic model? It says the model which incorporates the details of intercellular metabolism are referred as structured models, and such models accounts for unbalanced growth of microorganisms. For example, when the composition of major cellular constituents like RNA, enzyme vary as a result of changing the environmental conditions. So, structured model is a unbalanced growth in kinetics, and you just see there is a unbalanced growth is applicable in the batch growth, in the fed batch growth, and in transient situation in the continuous culture or well mixed bioreactors. Now, we can quickly understand in the case of unstructured model, it describes only the quantity of biological phases. It do not represent about the quality of biological phases. In addition, it is unable to predict the dynamic behavior of the cell that is subject to changing the external conditions. So, for this, if the changes in the biophase is significant with subject to change in the external condition, then we have to apply the structured model. It says when cell population changes significantly and these compositional changes further influences the kinetics of substrate utilization, product formation, then one has to apply the structured model. But as we discussed earlier, in the case of enzyme catalysis, the synthesis of enzyme is taking longer time. In that case, the enzyme concentration can be considered constant because the enzyme catalysis is taking place in the time scale of seconds or so. So, we have to compare this with respect to environmental changes, how fast is dynamic behavior changing, and if it is significant, then we have to use the structured kinetic model. Further, it is important that which process we are talking about, and whether it is matching with genetic system time scale, epigenetic system time scale or metabolic system time scale. So, one example, let us say you are having a biophase, biomass, its mass is x j or molar composition of a j compound is the C j. So, how we are going to write this? Let us say you write this mass balance of the reactor. So, what is coming in is 1 upon rho c is mass density of the cell into phi x is the mass of cell added into reactor and composition is C j, plus generation, what will be generation? 1 upon rho c volume of the reactor x into molar rate of formation or Fi, rate of formation, this equals to the rate of accumulation d upon dt 1 upon rho c V x into C j. So, we are considering x is the total mass and C j is the fraction of j. Now, if you differentiate it, we are going to get this d C j upon dt into 1 upon rho c V r x plus dx upon dt into 1 upon rho c V r to C j. Now, if we consider this left hand side, then rho c will be cancelled out and V r will also be cancelled out from here and here. So, this V r can be cancelled out from here and here, and rho c will be cancelled out in all three. So, at the end we will left with d C j upon dt equals, this is R f I minus C j 1 upon x dx upon dt, this is going to the other side, plus phi x upon x into V r to C j. So, now if we just see here 1 upon x dx upon dt is mu. So, this is mu. So, it becomes d C j upon dt equals R f I minus mu into C j. Further, for time being we are putting the value of phi x as 0. So, we are considering that in the case of batch there is no input, and in the case of continuous we are assuming we are adding the sterile feed. So, there is no biomass in the feed. So, this term can be put at 0. So, we are seeing d C j upon dt equals to R f I minus mu into C j. So, it is depending on the both rate as well as the how specific growth rate is changing. Now, the first model we are going to discuss is the compartmental model. It says biomass is divided into a small number of components. For example, you consider the synthetic component and structural component. Synthetic component include RNA and structural component includes DNA and proteins, or you can say this assimilatory and synthetic components. Now, if we just see basis of system dynamics, so there are many events are ongoing like molecular collisions, biochemical reactions, diffusion, turnover of RNA, protein synthesis, increase in the cell number, completion of batch process, and there may be spontaneous mutations as well. Now, as we discussed earlier, these processes can be divided into 3 time scale, that is genetic, epigenetic and metabolic. So, each process has a characteristic relaxation time. So, what we can see here, the relationship between time scale of changes in the cell environment and the spectrum of relaxation time of cellular process. So, if you can see this ratio, so for the small relaxation time versus tau e may be considered in the quasi steady state as we discussed earlier, and on the other extreme the relaxation time of some cellular processes are very large as compared to tau e, and such processes are assumed to be frozen at initial state, because this relaxation time is much larger than the time scale of change in the cell environment. So, these are the two extremes. One is this smaller ratio of relaxation time versus time scale of change in the environment, and other extreme is this relaxation time are very large as compared to, that means you can say the very high value of relaxation time versus tau e ratio. Now, for many complicated systems, typically there are only 2 or 3 system relaxation time in the same range as the time scale for the environmental changes. So, this gives us the flexibility to consider this dynamic behavior into 2 or 3 components, and typically here we are going to consider, or here we are going to approximate the dynamics of a large system using 2 or 3 system variables. So, first model is Williams 2 compartment model. So, it reproduces the several aspects of batch growth dynamic well. So, here it considers a 2 systems, you can see the 2 compartment. First is synthetic portion is produced by the uptake of nutrient and with the yield coefficient of y. So, here the rate of cell synthesis component formation is first order of total cell density and nutrient mass concentration. So, we are considering this one as a first order. Now, the second one is the structural genetic cell component, and that is produced from the component 1 at a rate proportional to rho 1 and rho 2. So, what is the rho? The mass of I per unit volume of the cell. So, here this will be the rho 1, this will be rho 2, and the cell component produced from the component 1 at a rate proportional to the multiplication of or the product of rho 1 into rho 2. Now, next is doubling of component 2 is necessary and sufficient for cell division, and accordingly if we just see cell number density is proportional to the density of component 2 in the cell culture. It is very important, this cell number density is proportional to the density of component 2 in the culture. So, this is component 2, and in addition we are strictly considering biomass is comprised solely of component 1 and so 1 we are saying K component, that is synthetic pool, 2 that is the genetic component or G component, it comprises DNA and proteins. So, substrate intake takes place at the K component and G is the genetic pool, and we are considering this rho 1 and rho 2 of separate density, and if we sum them up, this comes the total density of the cell. So, here before we proceed further, we can do this mass balance, particularly for the substrate and overall biomass for a constant reactor volume VR. So, it says d into VR x upon dt, this equals, the rate constant is K1 into S, x and VR. So, what we are considering? We are considering the VR as a constant. So, we will see this dx upon dt equals K1 S into x, and K1 S upon x can be written as a mu. So, it is following a logistic equation. Similarly, if I write the mass balance for the substrate, so this will be ds upon dt. Again here we are considering Vr as a constant, otherwise we have to write ds into Vr upon dt equals, is considering the yield as y, yx upon s into K1 S x Vr, that is it. So, it says Vr will be cancelled out. So, ds upon dt is minus 1 upon y, K1 S x, s and x, that is it. So, only difference between these two is it is divided by the yield coefficient, and this yield is y x upon s. Now, we will first do the mass balance on the component G. See the K, see the G, substrate is coming, rate here is the K1, here the rate is K2, and density is the rho 1 and rho 2. So, if I write the mass balance of component G, so this is going to be d into rho 2, and in addition to rho 2, we need to write a term that is x, and what will be the x here? X will be the, this will be the concentration per cell. So, how we can find the concentration per cell? So, this we can have the cell divided by its total cell volume per unit reactor volume. So, you can divide with this density. So, because density is cell density, it means cell mass per unit volume. So, we are having cell mass per unit volume. If we divide, so we will get this volume here. So, d rho 2 for component 2 x c, you can write like this as well. This will be equals to K2, and what we discussed initially was how the product formation is taking place. If you remember here, we have discussed the structural component is produced from the component 1 at the rate proportional to the product of rho 1 and rho 2. So, K2 into rho 1 into rho 2, and this component x upon rho c upon dt, right. So, we can expand this term. So, this will be x upon rho c d rho 2 upon dt plus rho 2 into d x upon rho c upon dt, and this is equals to the K2 rho 1 rho 2 x upon rho c. Now, we can only keep d rho 2 upon dt at the left hand side. So, it will be d rho 2 upon dt. Now, this will be equals to right hand side K2 into rho 1 rho 2, this term will be there, minus this will go to the other side. So, this will be rho 2, rho c will be cancelled out. So, this will be 1 upon x dx upon dt. And what is this 1 upon x dx upon dt is mu, that is equals to k1 into s. So, what we are writing, you are getting this k2 rho 1 rho 2 minus k1 s into rho 2. So, this is what we got here, mass balance on the G. Further, if you want to write in terms of fraction, so let us say if we say F2 is divided by, we have already discussed this rho 1 plus rho 2 equals rho c. So, if I say need to write the fraction F2, this will be rho 2 upon rho c. So, now this equation we can write in terms of fraction. So, this will be dF2 upon dt equals, here this rho 2, this will be F2, this will be 1 minus F2 k2 into rho c, and this term will be k1 into s into rho 2 will replaced by F2. So, this can be written in terms of rho 2, it can also be written in terms of F2. Now, let us go to the mass balance on component K. So, if I write the mass balance on component K, so it will be d rho 1 x upon similar rho c divided by dt. Now, this will be equals to the k1 into s rho c into x minus k2, it is also going to other side, k2 rho 1 rho 2 into x. Similar what we did in the last slide, we can have to expand this differentiation. So, this will be d rho 1 upon dt into x upon rho c plus rho 1 into dx upon rho c upon dt, this equals to k1 s rho c into x minus k2 rho 1 rho 2 into x. Now, if we rearrange, what will happen, this term will you are going to get dx upon dt into 1 upon x. So, at the end you will end up getting this term, this k1 s. So, this is the mu, right. If we just rearrange this is the mu, mu equals to the k1 s to rho 1, do you understand? And here there is a term k1 s into rho c. So, rho c will be rho 1 plus rho 2. So, ultimately what will happen, this rho 1 term will be cancelled out. So, we'll end up with, so you just see this rho 1 term will be cancelled with this. So, we will end up with k1 s rho 2 minus k2 into rho 1 rho 2. Now, if you remember the last slide, what was the value, d rho 2 upon dt was k2 rho 1 rho 2 minus k1 s into rho 2. So, what it says is, if you simply sum them up, d rho 1 upon dt plus d rho 2 upon dt, this will be equals to 0, or you can say d rho 1 upon dt equals to minus d rho 2 upon dt. So, in this way you just see you have divided cell into these two this compartment, and how this rate is this linked with each other. Further, if you want to calculate how the substrate concentration is changing, the one easy way is to consider these two equations. If I simply sum them up, let us say this equation 1 and this equation 2, if I simply sum them up, so I can sum d x plus, here we have to multiply with y then this term will be 0, right. So, you have to multiply with y(s) into s divided by dt, this becomes 0. So, what it says is x plus y(s) into s equals to x naught plus y(s) into s naught. Now, this enables us to solve and get the value of substrate concentration, how it varies with the time. Just see, cell number is proportional to the density of component 2. The component 2 is root 2, right. Now, you have know how to calculate the substrate. So, you just see these are the parameters. K1 was 0.0125, K2 into rho c was 0.025, Y was 0.5, X naught was 0.05, S naught 1 and F2 at naught equals to 1. So, for given these two, we can solve these equations with the given boundary condition, and this is the typical profile. You just see substrate concentration, this is changing. Further, the cell number, as we discussed earlier, cell number is proportional to density of component 2. So, this will be density of component 2 rho 2 into x here, rho 2 into x upon rho c. So, you just see the cell number is also increasing and reaching to the plateau, similar to the concentration of biomass. Similarly, one can calculate cell volume also. Cell volume will be rho 1 upon rho 2 upon rho 1, or you can say rho c upon rho 1. So, what we are seeing, if you just see the profile here, at the initial there is a slow growth of the cell number, but the cell size increases rapidly, and further the cell size is reaching out to the 0, and cell size is proportional to the, and the cell number is proportional to the rho 2. Now, it is interesting to see here, you can observe the lag phase here, exponential phase here and saturation phase here. So, this is a typical batch profile which actually occurs during this bioprocess, and substrate profile is depleting. So, if you just see this model, what is predicted? It predicted the existence of lag phase in which the cell size increases, and exponential growth phase where the cell size is maximum. You just see during the exponential phase it got the maximum value and further it declines. Third, that this stationary phase is with relatively small cells. We are having this cell size is smaller during this stationary phase. And it is important, the change in the composition of cell is occurring during this growth cycle, and since these changes are evident during the exponential phase, apparent growth is not exactly balanced. So, you can say this is a unbalanced growth. Now, if you just see the prediction of this model, it is able to predict the experimental data quite well, but at the same time this cell number that is proportional to the density of the component 2 that is reaching to the total biomass concentration. So, that should not be the case, because the biomass is composed of both the component, this component 1 as well as the component 2. So, these are the some limitation of this Williams 2 component model. So, followed by that, the next model we are going to discuss here is Ramkrishna's 2 component model. So, similar to the previous one, they are considering 2 pools, or you can say one is the G mass, other is D mass. Now, what is changed here is, in the earlier case the first component was comprising only the RNA. Here the G mass will comprises RNA and DNA, and D mass comprises proteins And in addition, there are some inhibitors which inhibitor T that deactivates both. So, you can see these are the quick reactions in the G mass. The first component that will interact with the substrate. So, let us say AS into S plus D, this gives 2G plus T plus AT into T. So, what we are seeing here is in the first reaction D mass catalyzes the formation of G mass consuming AS unit of substrate and producing this undesired AT unit of unidentified inhibitor T. Now, in the second reaction further what is happening, G, this is the AS dash, G plus AS dash AS plus D, this is leading in the second reaction, G mass now catalyzes the formation of D mass. So, there will be 2D plus G plus AT dash into T. So, here again AT dash fraction of inhibitor is produced, and if you just see the last two reaction, it says G plus T inhibitor is preparing the inactive form of G plus 1 plus A T inhibitor into T, or this G plus D plus T producing N D plus 1 plus A T I dash into T. So, what it says in the last two equations shows that both G and D mass are deactivated by the inhibitor and they are producing their inactive form Ng and Nd, and the rate of expression assumed in the model for production of G and D mass are double substrate form of equation. You can see we are considering this double substrate in one equation. The similar what we discussed for the Williams model, this mass balance equation for both batch and continuous culture can be written from here. Can be written from here, and for this activation or the deactivation we are considering here this model considers the first order for the deactivations. So, it considers the double substrate monad, you can say model for the G and D formation and first order for the deactivation. Considering this you can write the rate equation and mass equation, and that can be solved to predict the model parameter and can be compared with experimental data. So, what is expected that this model can predict oscillatory behavior about a steady state. I will stop here, and in the next lecture we will be discussing the model of cellular energetics and metabolism. Thank you so much.